Okay, the past couple of weeks, actually, I guess just a week, we've been talking about electromagnetic waves, and this podcast is going to be spending a little bit more time talking specifically about waves and the characteristics of waves, but also talking a little bit more about light and about sound waves. These notes are going to go on page 23 in your interactive notebook, and you can set up your notes just regular Cornell style for writing these particular notes. One of the things we haven't yet talked about too much is what exactly a wave is. And so I'd like you to write down a definition of a wave. It is a disturbance that travels through matter or space, and it carries energy. So a wave is carrying energy. It is not carrying matter. It is just energy that's moving through a substance, or it's carried by a substance. Now, if the wave is passing through matter, not empty space, then it travels through matter. It's being carried along, and that matter that's carrying it we call the wave medium. So if you think about something that most people are familiar with, which is the wave at the football game or a baseball game, when everybody in the stands does the wave, you can think about how the people in the stadium are the wave medium. In other words, the people in the stadium are carrying the wave, but the people aren't moving, just the wave is moving. So in other words, each person in the stadium that's participating in the wave, all they're doing is standing up and sitting down, right? If you've been part of this, you know that all you do is you stand up with your hands in the air, you go, woo, and then you sit back down. But the wave is traveling all the way around the whole stadium. So the wave is carrying the energy of all the people going up and down, but the actual people that are carrying the wave, they're not going all the way around. They're just standing up and down. So the people are the wave medium, and the wave itself is just the energy of the motion of the wave. Now, there are two kinds of waves that we're going to talk about, two types. The first type is a transverse wave. So some waves are called transverse, and in a transverse wave, the particles in the medium, so these particles that are moving perpendicular or up and down, compared to where the energy of the wave is going. So in this example, the wave is traveling that way, but the actual medium, the particles, or in this case the rope, is actually moving this way. So that's perpendicular. So the example I gave a minute ago of the wave at the football game, this is a transverse wave because the people are moving up and down and the wave's going round and round. So this is called a transverse wave. Now, one of the things you need to know, and you might actually even draw this in your notes, is that transverse waves have these parts to them. Transverse waves have a crest, which is the highest point in the wave. They have a trough, which is the lowest point in the wave. So this point right down there is the trough, and this point right there is the crest. And then they have something called the amplitude, which is the distance between the midpoint of the wave, which is represented by this line right here, that's the midpoint, the distance between there and the crest or the trough is the amplitude. It's the height of the wave, but it's measured from the medium part of the wave all the way to either the highest or the lowest point. That's the amplitude. And then we have the wavelength, which is the distance between any 2 points of the same points on the wave. The easiest way to think about it is from crest to crest or from trough to trough, but it can be measured from any place on the wave. But it's easier to think about it from crest to crest or from trough to trough. But that's the wavelength, that's the length of the wave. So those four parts you definitely need to know. Now, light waves are transverse waves. So we've been talking quite a bit about light and about electromagnetic radiation that comes from the sun. That's all kinds of those electromagnetic waves, from radio waves all the way to gamma rays, are all transverse. So the energy in the wave is moving perpendicular to the wave itself. And so we represent them by these waves that are shown here. Now, the relationship between those parts of the wave and light waves are like this. The amplitude of the wave is the brightness. So a higher amplitude wave is a brighter light. So here we have a high amplitude wave. Here we would have a low amplitude wave. The frequency and wavelength that we talked about determine the color of the light. And we've talked about this before. A high frequency wave like this would be blue. A low frequency light wave would be red. Now we talked about this a little bit also. We talked about how light can be reflected, absorbed, and refracted. When light is reflected, of course, it bounces off. The wave strikes an object and it returns back. It bounces back to your eye. Now, it usually bounces in all directions unless it's a mirror. A mirror bounces straight back, but most objects bounce the light in all different directions. But remember, colored objects reflect their own color. So remember we talked about how the apple reflects red light and absorbs others. And that brings us to the next one. Light can be absorbed. So first, light can be reflected, light can be absorbed. Remember, we talked about how light is absorbed by certain objects, and that whatever light is absorbed, that's not the color of the object. That's the light that we don't see. And we talked about how white objects reflect all light, but black objects absorb all of the light. And that's why we see them as black, because they're not reflecting back the light. And then finally, light can be refracted, and we already talked about this as well, about how light waves will change direction when they pass from one substance to another. So from light to glass, from glass to light, from air to glass, from air to water, from water to air, things like that. When they're passing from one substance to another, they slightly change direction. And this is, of course, how white light can be separated into a rainbow through a prism, or how come an object placed in water sometimes looks like it's not exactly where it should be as it passes to the water, because that light is being refracted. The light coming from the spoon is actually bending or changing direction when it passes from the water to the air. Now, that's all I had to say about transverse waves. We're moving on to the second type of wave now. It's a longitudinal wave. It's also called a compressional wave. And I think your book calls it a compressional wave, but other people sometimes also call it a longitudinal wave. Now, in a longitudinal wave, the particles in the medium, okay, remember we have a medium that is carrying the energy of the wave. The particles in that medium, instead of moving up and down as the wave passes by, they're moving the same direction, parallel. I call this a back and forth wave. Okay, so if the wave energy of this wave here is traveling to the right, the particles are moving back and forth from right to left. Okay, you notice it looks very different. This is supposed to represent a spring or something like that, but a longitudinal wave is like a back and forth wave. Now, I don't know if you've ever played with a slinky, but slinkies really help us to understand longitudinal waves, because you can compress the slinky and then let it go, and you can see a wave travel, and we'll be doing that in class on Tuesday. Yes, on Tuesday. But compressions are the areas where the particles are pressed together, and these things called rarefactions are where the particles are more spread out. So you can see in this diagram of the spring, we have a compression, and then a compression, and then a compression, and then the area in between where the particles seem to be more spread out, or in this case the slinky or the spring is more spread out, that's called a rarefaction. And the way a compressional wave or a longitudinal wave works is that you have areas that are compressed, like here, and then they release and they form a rarefaction, and then this compressional section ends up moving along as each little section presses the next section. So the most obvious example of this, and the one that you really need to understand, is sound waves. Sound waves are very different from light waves because, first of all, something has to vibrate in order for there to be a sound wave. There has to be a medium. There has to be some kind of particles. Light waves can travel through empty space, but sound has to have particles. That's why it's so different. But what happens is there's a vibration, and the vibration compresses air particles or water particles, and as they're compressed, they press against the next little section of air or water, and that compresses them, and so forth and so on. And so there's particles that are actually sort of vibrating back and forth and pressing other particles, so that this energy that's carried by the vibration is traveling. But of course, remember, the particles are just moving back and forth. They're just vibrating a little bit. We'll talk more about this because I feel like I'm not explaining it very well, but we'll have to talk about it more in class. But just remember, sound waves require a medium. They require some matter to travel through. It can be air or water or even some other substance, a solid. Sound can travel through a solid, and we'll have a little activity in class where you can observe that. Now, this was a popular movie quite a while ago. It's still kind of a classic movie, Alien. If you've never seen it, you need to watch it because it's really scary and good. But the tagline for this movie was, "In space, no one can hear you scream." I want you to think about whether or not that's true. And if it's true, why is it true? So, in fact, it is true. And the reason why is because in space, it's a vacuum. There's no particles. There's no matter. There's no air. There's no water. There's no solid. There's no nothing. And so sound can't travel in space. You could scream all you wanted to if you were in space and no one would hear you because there's no particles to carry the sound wave. You would attempt to vibrate, but there would be nothing to vibrate to carry the energy. So sound waves require a medium, unlike light waves, which do not. So you can see light in space, you cannot hear sound. Now, when we talk about some of those parts of the wave that we discussed with the transverse wave, we can talk about similar things with sound waves. When we talk about the amplitude of a sound wave, we're talking about how loud the sound is. Okay, the louder the sound, the higher the amplitude. So if I talk really loud, that's a high amplitude. If I talk really soft, that's a low amplitude. Then we can talk about the frequency of the sound wave, and that determines the pitch, the high or low sound. If you play music, you know what pitch is, but maybe not everyone plays music and knows about music. But if there's a high frequency, we can say that's a high note, like a soprano would sing, like, oh, really high. That's not really that high, but you get what I'm trying to say. A low frequency would be like a tenor or something, and that might be a low note, like, oh. That would be maybe a lower frequency. And remember, if it's a high amplitude, then it's very, very loud. Okay, once again, we can talk about reflection, absorption, and refraction of sound, because these three are true for all waves, not just light waves. If sound is reflected, we call that an echo. So in an echo, the sound waves are transmitted. A vibration starts a sound wave. It's transmitted through the air or maybe through water. It strikes a surface where it cannot continue to travel, some kind of object that won't allow it to keep going, and it will bounce back. And then you hear the sound again a few seconds later. Sound can also be absorbed, and there are some substances that are better at absorbing sound. And remember, when a wave is absorbed, that energy is taken in by the substance and it's converted into thermal energy, and the wave is gone. This is an example of kind of one of those soundproof rooms, they call them. Like they have them on TV game shows sometimes, or they use them in music studios in certain places so that they can absorb the sound. Maybe they'll put it on the outside of the sound booth where they're doing the musical recording, so that sounds that are going on outside of where the musicians are don't interfere with the recording that they're making of the musician. And you want that. You want sounds to be absorbed so you don't hear those extra sounds. And then sounds also can be refracted, and this is a little less common, but I don't know if you've ever noticed that when it's nighttime, it seems like you can hear sounds better. And the reason is because, kind of like what's shown here in this diagram, when warm air is at the surface, the sound waves are actually moving slower in the cool air and faster in the warm air, and so it actually bends the sound wave, and you really miss some of that sound if you're listening. At nighttime, the surface of the earth is cooler and the air is warmer above the surface, and it actually makes the sound wave bend the other direction, and so at night you really do hear things better. In fact, they say that this occurs over the surface of a lake, and that sometimes, depending on the size of the lake, you can hear people at night all the way on the other side of the lake. You can hear clearly what they're talking about. It's kind of cool. I don't know if that's really true, but it's kind of cool. Okay, and here's the summary, and then I'll be done. First, waves can be transverse or longitudinal. Those are our two types. Second, waves have amplitudes, wavelengths, and frequencies. And we also talked about crests and troughs. Number 3, light waves are transverse and sound waves are longitudinal. And finally, both kinds of waves show reflection, refraction, and absorption. Thanks for listening all the way to the bitter end of the podcast, and I hope you got some good notes. Bye-bye.
Made with Doodlecast Pro.